Why is GPT important, and what are the use cases of GPT? GPT stands for Generative Pre-trained Transformer. G for generative. The model can generate new text given a prompt. It predicts and produces coherent continuations rather than just labeling or classifying text. P for pre-trained. It is pre-trained on massive amounts of publicly available text from the internet using unsupervised learning before being fine-tuned for specific tasks. And T for transformer. GPT is based on the Transformer architecture introduced in Attention is All You Need from 2017, which uses the self-attention mechanism to understand the relationships between words in a sequence. You can create engaging social media content, posts, captions, and attention-grabbing text. Convert text into different styles, write and learn code, analyze data, interpret information, and provide quick insights. Produce learning materials, lessons, summaries, and study guides. Build interactive voice assistants, chatbots and voice bots that understand and respond naturally. The first version of GPT was introduced in 2018 by OpenAI with 117 million parameters. It consisted of 12 transformer layers, each with 768 hidden units and 12 attention heads. In 2019, GPT-2 marked a significant leap forward, increasing the model size to up to 1.5 billion parameters. It demonstrated a strong ability to generate coherent and contextually consistent text over long passages. In 2020, with 175 billion parameters, GPT-3 became one of the most powerful language models ever created at the time. It could perform a wide variety of language tasks, such as translation, summarization, and question answering, without requiring task-specific training. GPT-4 in 2023 continued the trend of rapid advancement, although its exact parameter count was not publicly disclosed. It is significantly more capable than GPT-3, offering greater accuracy, contextual understanding, and reasoning abilities. GPT is trained in two main stages using large-scale text data. First stage is pre-training. In this stage, GPT learns the basic structure and patterns of human language by processing massive amounts of text from the internet. Causal language modeling, CLM, is applied here. The model learns to predict the next word in a sentence using only the previous words, not the ones ahead. GPT is an autoregressive modeling, meaning it generates one token at a time, where each token depends only on the tokens before it. To enforce causality, GPT uses a self-attention mechanism that is masked, meaning each word can attend to, or see, only itself and the words before it. It cannot look ahead at future words in the sentence. Why causal? Because there is a strict cause-effect relationship. What comes before causes what comes next. No backward flow of information is allowed, mimicking the natural flow of how we speak or write. You can think of GPT like a super advanced autocorrect function in your phone, not just fixing typos, but generating full, coherent sentences by predicting the most likely next word based on context. So, in the second stage, fine-tuning, the model can be further trained on specific data sets that specialize in certain tasks. For example, summarization, question answering, programming help, and more. Before we dive into GPT Architecture explained visually, I'd like to thank today's sponsor, ProjectPro. ProjectPro is an amazing platform that offers hands-on practical courses for data science, machine learning, and AI professionals. If you're interested in GPT and want to go beyond the theory, ProjectPro has real-world projects that show you how to implement GPT models in actual production environments, from training to fine-tuning and deployment. Whether you're just getting started or looking to level up your AI skills with practical experience, ProjectPro gives you access to a rich library of guided projects created by industry experts. ProjectPro's Gen AI Accelerator program masters generative AI through hands-on, real-world projects with ProjectPro. This accelerator offers guided learning in NLP, computer vision, AI agents, and more, all supported by expert mentorship and practical experience. Fast-track your AI career. Apply now and build with Gen AI. Now, let's get back to our architecture and see how GPT really works under the hood. In the first step, we take the raw input text and tokenize it, breaking the sentence into smaller units called tokens, which can be whole words or subwords. Andrew is playing with the dog in the park. Each token is mapped to a unique ID number, integer, from the model's vocabulary. The word Andrew has the ID 101. The word is has the ID 205, and so on. Next, these tokens are converted into embeddings, numerical vectors that the transformer can understand and process. These vectors encode semantic meaning. Similar words have similar vectors. Positional encoding, keeping word order. Transformers don't understand word order naturally, so we add positional encoding. This tells the model where each token is in the sentence. Dog is playing with Andrew is different from Andrew is playing with the dog. Dropout layer prevents overfitting, meaning it stops the model from memorizing the training data. It occurs when a model learns the training data too well, including its noise and random fluctuations. To avoid overfitting during training, a dropout layer randomly turns off some neurons. Think of a soccer team. If some players are randomly taken off the field at each practice, the rest learn to play well no matter who is missing. This makes the team stronger and more flexible. Or, you can imagine a class with 10 students, which are the neurons, working together to solve a problem. Without dropout, when all the students work every day, they rely on the smartest one, and the others don't learn much. With dropout, every day, 3 students are randomly sent home, and the rest have to manage on their own. In this way, everyone learns to collaborate. Example with dog. If the vector for dog has 10 numbers, dropout might randomly set 20% of them to 0 for one training pass. This forces the model not to rely too much on any single neuron or feature of the word dog. It must find many ways to understand the meaning. Transformer blocks. This is where the real magic of understanding context happens. Layer normalization. Normalization adjusts numbers to be comparable, like a fair scale, so none are too huge or tiny. Multi-head masked self-attention is the core of GPT. Multi-head means the model performs multiple attention operations in parallel, learning different relationships from different angles. The model learns which words in the input are important to each other, using masked attention. GPT is an autoregressive model. That means it can only look at previous tokens, not future ones. Each token attends only to itself and those that came before it. For example, when processing the word dog, the model can look at Andrew is playing with the, but not in the park. The softmax function converts the raw output vectors into probabilities. All probabilities together sum up to 100%. Which makes it easy to interpret them as likelihoods of each possible next token. Dog receives the highest attention, 25.96%. The most important word for predicting park and in also get strong attention. They finalize the location phrase. Playing is relevant to the sentence's verb or action. Articles and prepositions like the, with get lower attention. Andrew, the subject, is least relevant at this stage. Drop out again to prevent overfitting. Each attention head in the multi-head attention mechanism captures different relationships and patterns within the input sequence, essentially offering a unique perspective on the data. These individual outputs are then concatenated into a single long vector that brings together all these perspectives. This concatenated vector is passed through a linear layer which learns how to effectively combine the information from all heads into a unified, meaningful representation. In doing so, the model integrates the diverse insights from each head and transforms them into a consistent output of the expected dimensionality. Drop out again to prevent overfitting. Residual connection. The attention output is added to the original input, residual connection, helping the model preserve and refine earlier info. Layer normalization. Neural networks can become unstable if the numbers flowing through them are too big or too small. Normalization keeps things balanced. Feed-forward network FFN. After the second layer norm block, you will find the following layers: linear layer, Gallo activation function, and linear layer again. These 3 layers, connected in this order, form the feed-forward network subblock within a transformer block. They are responsible for the linear transformation of contextual representations, allowing the model to capture nonlinear relationships in the data. What exactly does the feed-forward network do? The feed-forward network takes the vector of each word, already enriched with contextual information after attention, and processes it individually to refine and transform it into a higher level, more abstract meaning. In our sentence, Andrew is playing with a dog in the park. When the model processes the token dog, it already knows from self-attention that Andrew and playing are important for understanding what the dog is doing. Now feed-forward network comes into play and does this. The vector for dog already includes influence from Andrew, playing, and in the park. The feed-forward network passes it through again to the first linear layer, which it increases the dimensionality of the vector, giving it more mental space to think. The JLU function activates relevant features or signals like an animal involved in playful activity outdoors. And then the second linear layer compresses the activated information into a compact, refined representation, now more meaningful and abstract. We have the following result. The vector for dog no longer just means a dog. It now means a dog playing with Andrew in a park. Imagine that feed-forward network is each word's internal processor. Andrew thinks, I'm the one playing. Dog thinks, I'm involved in the play with Andrew, in the park. Park thinks, this is where the action happens, involving Andre and the dog. The feed-forward network helps each word interpret what it learned from attention, preparing it to contribute properly to the next word prediction. Dropout is applied again after the feed-forward network to avoid overfitting and improve reliability. Layer stack means more blocks, meaning deeper understanding. These transformer blocks are stacked on top of each other, usually 6, 12, 24, or even more. Each additional layer lets the model understand more complex patterns and dependencies in the text. The more layers, the deeper the thinking. The final layer, normalization, prepares the output for the next step. Linear projection to vocabulary space. Each output vector becomes a list of Logit's raw scores, one per word.
The transformer model generates for each position in the sentence a numerical vector, for example of size 768 or 1024, called D model. This vector then needs to be transformed into a format that can select a real word from the model's vocabulary, for example 50,000 possible words or tokens. To do this, a linear layer is applied, which transforms the vector from size D model into a vector of size vocab size, meaning one score for each possible word tokenizer in the vocabulary. Softmax turns scores into probabilities. For example, after processing the input, Andrew is playing with the dog in the model chooses park as the next word. In the final output layer, the model decides what to generate next. Thanks for watching.